So good morning, students. Yesterday, due to some emergency meeting, I couldn't complete the class. So let's continue with the topic. So after solving that problem, like you will be knowing how to find out the equilibrium count or how to find out the average speed if some data like degree of the curve or if you are having a set of values of uh, number of trains and their corresponding uh, velocity or speed. Okay, so now let's move to count x's. So in the last classes we have discussed about what exactly is Kant or super elevation, and after that we have discussed about the Kant deficiency, right? Not always we will be able to provide the theoretical Kant on a railway track section. So whenever we are reducing the Kant from the theoretical value and we are providing some less amount of Kant, then there will be a Kant deficiency that we have discussed in the last class. Now let's see what is Kant excess. Okay? So whenever a train is negotiating a curved track uh, at a lower speed, which is even lower than the equilibrium speed, then the Kant excess occurs in fact, because for each Kant the train should be traveling in a corresponding speed. Then only the train will be able to negotiate the curve smoothly at that particular speed. So if a train is moving at a lower speed, which is even lower than or which is even less than the equilibrium speed for that track, then that train will be experiencing some difficulty while negotiating the curve. And this is because of the Kant excess. Okay. So in short, we can say that the difference between the actual count provided and the theoretical count required for the slower running trains or the theoretical count required for such lower speeds is known as count excess. And for Indian Railways, we have given a maximum value for count excess. So in no case the count excess value should be more than these standard values. And coming to broad gauge, the maximum count excess should be 75 mm and maximum count excess in the case of meter gauge is 65 mm. Now here comes the next term, negative superelevation. Okay, so as you can see in this figure, you can see a straight, a single line track, a main track is approaching, right? And at this point, it is getting diverted into two tracks. One track acts as the main line and the other track acts as the branch line, right? So here you can see. Okay. So let's first of all consider the main line. So this was the actual single line track, right? And at this point, the track is getting diverged. So this is the main line, okay? And this AB is the outer rail of the main line, and CD is the inner rail of the track section, okay? And what we have mentioned in the last class, the inner rail level will be maintained as such, or it is the reference rail, and the outer rail will be elevated with respect to the inner rail. So from A to B, it will be raised above when compared to C to D. Okay, so this C will be having the same level as that of the level track, but from A point till B point, we are providing a gradual increase in the elevation so that at somewhat midpoint it will be exactly small theoretical count itself. Okay, so from this it is very clear that the point A is at a higher elevation when compared to point C. Okay, now let's take the branch line. Okay, coming to branch line, C to F, it is the outer rail. Okay, and from A to E is the inner rail. That means AE, the line AE, curved track AE is the reference rail and CF is the elevated rail, right? Which means A is maintaining the same level as that of the single line track and C is elevated. Okay. So when we considered mainline, we told A is at a higher point when compared to C, and when we are considering branch line, we are saying C is at a higher elevation than A, point A, right? Which is contradictory, right? Which is not at all possible with the help of a single layout. So in a single layout, this cannot be achieved. If you are separating both things, that's fine. Okay. If a single line is coming and you are taking a left turn, yeah, that is possible. A will be in a level ground and C will be elevated. And if you are considering another track coming and diverting to right side, okay, or negotiating a curve, then when compared to C, A will be in a higher point. But when you combine everything and when a single track is getting diverted to a main line and branch line, this cannot be met. Okay. So in such situation, what happens is that we will give priority to main line. Okay. So C will be on a level surface and A will be on a higher, comparatively higher point compared to C. So when you are providing or when you are giving priority to main line, the branch line will be having a negative super elevation. Okay, you cannot meet all these things in that branch line. So in that branch line, you will have to provide a negative super elevation. The value of super elevation will be minus. That's why we are calling it as negative super elevation. And also, another thing that you should be aware is that the speed of the train traveling on both these tracks must be restricted, and it should be restricted especially on branch line because we have provided negative super elevation over there. Okay, now let's see how to provide negative super elevation. So the equilibrium super elevation for the branch line curve is first calculated using the formula E is equal to GD square by 127 R meters. Okay, so this is a standard formula, but when it comes to road gauge, you will have 1.315 E square by R. That much centimeters. If you're using the standard thing, you should keep in mind that the elevation, super elevation is in meters, but if you are using our specific equations formulas, then the super elevation is expressed in centimeters. Okay, so in order to provide negative super elevation, the first step is to find out the equilibrium super elevation from this formula. Okay, so you are going to find the super elevation for your branch line. The next step, the equilibrium super elevation E. So from the first step, you will be calculating the equilibrium super elevation, and from this E, you are reducing the permissible Kant deficiency, okay, depending upon the type of the track. So E minus CD you are doing to get the resultant super elevation. Okay, that is X is equal to E minus CD, where E is the equilibrium super elevation and CD is the Kahn deficiency. And the resultant super elevation is expressed as or denoted by the letter small x. Elevation, equilibrium super elevation, and CD Kahn deficiency. For broad gauge, it is 75 mm. So, if it is not mentioned in the question about the CD values, okay, then you have to consider this maximum permissible Kahn deficiency for broad gauge as 75 mm, and if it is a meter gauge, you can provide it as 50 mm. Okay, and since we are calculating the negative super elevation, the CD value, okay, CD value is generally higher than that of the super elevation, and finally your x, what you are calculating for your x, will be a negative value. Okay, so the resultant super elevation will be negative. Now let's move to the calculation of safe speed, which is suggested by or recommended by Railway Board. So here you can see a set of formulas for the different types of gauges. Okay, so whether it is a broad gauge or meter gauge, then you can go for both these equations. V is equal to 4.35 square root of r minus 67, and second equation is V is equal to 4.4 square root of r minus 70. Whether you are considering first equation or second equation, it doesn't matter. Stick on to any of the equation. ഏതെങ്കിലും ഒരു ഇക്വേഷനിലേക്ക് മാത്രം സ്റ്റിക്ക് ചെയ്യുക, രണ്ടും കൂടി മിക്സ് ചെയ്യരുത്. Okay. So if you are sticking to first equation, okay, solve the problem with the first equation itself. Broad gauge ആണെങ്കിലും meter gauge ആണെങ്കിലും, you can go for any of these equations. And if it is a narrow gauge, then you have to go with these two, either any of these two equations. That is V is equal to 3.60 square root of R minus 6.1, or else V is equal to 3.65 square root of R minus 6. So these are the standard equations to find out the safe speed. So earlier we used to find the um, speed from, you'll be able to find the equilibrium speed from the equilibrium current equation, which is E is equal to 1.315 V square by R in the case of broad gauge, right? So let's solve another problem. All of you take down this question. On a broad gauge 3-degree curve, the equilibrium current is provided for a speed of 70 kmph. Okay. Now calculate the equilibrium current allowing a maximum current efficiency. What would be the maximum permissible speed on the track? This is the question. You are given a railway track section with a horizontal curve of 3 degree. It is a broad gauge track. Okay. So you are asked to find out the equilibrium current, and the speed of the train is 70 kmph. Okay. And you can provide maximum current efficiency. And if you are providing a maximum current efficiency, what would be the maximum permissible speed on this track? So two things you need to find: uh, equilibrium current as well as the maximum permissible speed on the track. Let's go into the solution. Given data. So these are the given data: 3-degree curve, broad gauge, and velocity or speed is 70 kmph. Then from this you will be able to find out what is the radius of the curve. Equation is 1720 divided by d. Okay, all of you, so you have to substitute it and find out the answer. Okay, and verify the answer. And next step is to find out the equilibrium current. And since it is a broad gauge, you can directly go with this equation. E is equal to 1.315 V square by R. Substitute the value of V and R in this equation and check whether you got this as the answer. Okay. And next is theoretical count. Okay, so we have when we discussed about count efficiency, we discussed that theoretical count minus actual count will give you the count efficiency, right? And actual count, what we are giving in reality is nothing but the equilibrium count itself. Okay, so from that we are arriving in this expression, that is theoretical count is equal to equilibrium count plus count efficiency. Okay, and count efficiency, here we have expressed the equilibrium count in centimeters, and the maximum count efficiency for broad gauge is 75 mm. So instead of 75 mm you need to convert it into centimeter here, because we have considered equilibrium count in centimeters. So adding both these things, you will get theoretical count as 18.74 centimeters. Okay, now let's find out the permissible speed for this corresponding theoretical count. Okay, and from where you are taking this, finding out this permissible speed from this equation itself. Okay, ഈ equation തന്നെയാണ് we are trying to find out. Substitute E value as 18.74. The speed is unknown. Then R is 573.3. Okay, so yes, we are using this equation to find out the permissible speed by substituting these values, 18.74 as the E value and 573.3 as the radius. Okay, and all of you please check whether you are getting this as the permissible speed. Okay, so in the question we had 70 kmph, and what we got after solving this problem is permissible speed as 90.4 kmph. Okay. Now we have our broad gauge. For broad gauge, the railway board has given this as the safe speed. Okay, so I am going with this equation. V is equal to 4.35 square root of R minus 67, and you can even go for the second equation, doesn't matter. Okay, substitute the value of R and you will be getting 98. Okay, so what does it mean? The safe speed is 98 kilometer per hour and permissible speed is only 90.4 kilometer per hour. Okay. So the maximum permissible speed is lower of the two values. Okay, so from this we can provide maximum permissible speed on that track is 90 kilometer per hour. Okay. And it is not yet finished. You need to write all these statements. Okay, here the track is designed for a speed of 70 kmph, sorry, which is less than the maximum permissible speed of 90 kmph. Hence, no speed limit sign is required for this track section. Okay, so let's move to the next problem. Again, another problem with a small difference. What would be the maximum permissible speed on the curve if on a 8-degree meter gauge track the average speed of different trains is 50 kmph and allowable count efficiency is half that of the maximum count efficiency. Okay. Here they have given a specific condition. Okay, you simply cannot take the maximum count efficiency, so the allowable count efficiency is half that of the maximum count efficiency. Okay, so let's see. Given data is an 8-degree curve, then meter gauge, average speed is 50 kmph. So you can follow the same steps as that of the previous problem. Find out the radius from this equation 1720 by d. So we'll be getting an answer. Next, equilibrium count, and this is meter gauge. So the equation is different. It is E is equal to 0.80 V square by R. So now you can see this by substituting the value of V as 50 and R as 212. 215, you'll be getting this answer. All of you please verify whether the answer is correct or not. And maximum super elevation, okay, for meter gauge, G by 10. That is how you are calculating Emax, right? The gauge width divided by 10 will give you the E maximum. So it is 10 centimeter for meter gauge, and again theoretical Kant is equal to equilibrium Kant plus Kant deficiency, and you can mention the condition given in the question. Allowable Kant deficiency CD is equal to 5 by 2, half the maximum value, right? So you'll get 2.5 centimeter as the allowable Kant deficiency. Now you can substitute this allowable Kant deficiency here, okay? What you got is allowable Kant deficiency, and this was the condition given in the question itself, and you are substituting this 2.5 over here. So you will be getting theoretical Kant is equal to 9.3. You have calculated 9.3 from here. 9.3 plus 2.5, which is 11.8. Okay. Now again, you can take this equation. Okay. From this equation, you can substitute the value of E as 11.8 and R as 215 in this equation and find out the permissible speed, capital V. You'll be getting some value. Okay. Verify whether it is 56.3 kilometer per hour itself. And for meter gauge, the railway board has given the equation as, for meter gauge and broad gauge, the equation is not different to find out the safe speed. You have got two equations. Take any of those equations. V is equal to 4.35 square root of R minus 67. ഏതെങ്കിലും ഒരു ഇക്വേഷൻ എടുത്താൽ മതി. രണ്ട് ഇക്വേഷൻ എടുത്തിട്ട് അതിൽ രണ്ടും സോൾവ് ചെയ്തിട്ട് നോക്കേണ്ട കാര്യമില്ല. കൺസിഡർ only one equation. Okay? So you can substitute the values and find out the safe speed. So safe speed is 53 kmph. And in the previous section we told that you can take the, from these two values you can consider the lowest value, right? Maximum permissible speed is 53 km per hour, and as the average speed of the train is 50 kmph, which is less than maximum permissible speed of 53 kmph, no sign speed limit signboard is required. Okay. Okay, thank you. So by this we have came to an end of railway engineering. Just go through these portions and understand it. Okay. Thank you.